So what were we talking about last time? Right, what was the demo that we did? I made a silvered flask. What? Tollin's reagent. That's exactly right. What is Tollin's reagent? There is a lot of letters there, but it's basically you start off with the solution of silver nitrate. Huh? It is an oxidizing agent. That's right. And what does it oxidize? Aldehydes to what? What do we get in the end? Carboxylic acids, right? So it adds an oxygen to an aldehyde and you get a carboxylic acid, right? And in the process, the silver is going from what oxidation state to what oxidation state? Positive 2? Positive 1. That's right. So it's going from a +1 oxidation state to a 0 oxidation state, meaning that it's undergoing reduction. And so the sugar that we were using was dextrose, and so dextrose is also known as a what sugar? It's a well, it is a simple sugar, that's true, but it's also a reducing sugar. And those reducing sugars are reducing because they're in equilibrium with what? So the sugar as the hemiketal form is in equilibrium with what? Remember the equilibrium up there? The open form, which has what functional group? The aldehyde. That's right. So you go from the hemiacetal to, or the hemiketal to the, actually it's the acetal, hemiacetal to the aldehyde. And that's an equilibrium process. And Le Chatelier's principles at play, right? Because as the aldehyde is formed, it gets oxidized with the Tollin's reagent, which forms the mirror, right? And you can oxidize the aldehyde all the way to the carboxylic acid eventually, right? So that's a new way to make carboxylic acids. We can oxidize aldehydes, right, with Tollin's reagent. And it's a fairly mild oxidizing agent, so it's pretty safe to use for a variety of things. But it is a standard test for determining whether or not you have aldehydes or reducing sugars. Okay, it works very well for both of those. And when you get into biochemistry or some higher level biologies, you will start to learn about the importance of reducing sugars in biological processes. So when they talk about reducing sugar, that's why it's a reducing sugar. It gives a positive Tollin's test. There's another test that they do. I think it's the Benedict's test, but same kind of process. It's just with copper. You can also reduce copper to copper metal. Another way that we can make carboxylic acids is through the use of Grignard reagents, right? And we talked a little bit about this. I think this is kind of probably where we left off, right? So we can make Grignard reagents from alkyl halides. What do you remember about the Grignard reagents in terms of the reactivity of the halides? Pardon? Okay, so bromine works really well, iodine works really well. What about chlorine? It'll work, but it's not. It's a little more difficult. What about fluorine? No, we can't make a Grignard with a fluoride, can we? So we can take alkyl chlorides, for example. Here's tert-butyl chloride, react it with magnesium and ether, and we can get the tert-butyl magnesium chloride, which is a Grignard reagent. How do Grignard reagents behave? They are very reactive. Okay, you're on the right track, but they don't behave like H minus, really. Well, carbon minus, right? So yeah, so they're like carbanions, right? And so are they nucleophiles or electrophiles? They are nucleophiles. Are they strong nucleophiles or weak nucleophiles? They're pretty strong. That's right. And so since they're nucleophiles, they're also what? They're also bases. That's exactly right. So Grignard reagents are also fairly strong bases. In this case, though, we would take the alkyl Grignard, in this case, or the aromatic Grignard, react them with carbon dioxide, and we can make carboxylic acids fairly easily, at least on paper. There's some technical difficulties working with gaseous carbon dioxide or getting truly dry ice to do the chemistry. But nonetheless, it is a reaction that can be done if you're particularly careful and know what you're doing. This week you all are going to do the Grignard reaction, right? Anybody have lab already? Yeah? Did you get your Grignard to work? You didn't finish? Pretty long? Did you see the Grignard initiate? Yeah? Okay, so you made the Grignard reagent. Yeah, okay, good. So it's a fairly straightforward reaction, but you have to be careful with moisture, right? Because of the basicity of the Grignard reagents. Now we know that nucleophiles will add to carbonyls, right? We've talked about this numerous times. So we can have a nucleophile attacking the carbon of the carbonyl. Why will it attack the carbon of the carbonyl and not the oxygen of the carbonyl? Say it. That's right. The carbon has a partial positive charge, and the oxygen has a partial negative charge. And so that makes that carbon electrophilic, right? This actually confuses a number of students sometimes, especially when I teach the larger class, because they go, well, I can push the nucleophile here and do the arrows just as easily, right? But the fact is it is wrong because the oxygen already has lone pairs on it. It's polarized. The oxygen has a partial negative charge. It's not an electrophile. Or it's not the electrophilic atom, I should say. The carbon of the carbonyl is the electrophile, okay? And so this is how we go from ketones, for example, or aldehydes to alcohols, right? So if we add a Grignard reagent, for example, to a ketone, what kind of alcohol do we get? We get a tertiary alcohol. If I take an aldehyde and I add a Grignard, what do I get, Delaney? I wouldn't get a primary. Well, I would if it was formaldehyde, but not just a typical aldehyde. What would I get? Secondary, that's right. Yeah, so we already know that we can do that type of chemistry, right? But when we're talking about carboxylic acid derivatives, we have some group here, X, that's electronegative, right? And so it turns out that we can actually do addition chemistry to the carbonyl followed by elimination, okay? And so it goes through this addition elimination step. And so, for example, we could take a nucleophile and react it with one of these carboxylic acid derivatives. You get the same tetrahedral intermediate that you get up here, okay? But instead of this being stable, this can now collapse, and X can leave as a leaving group, and you can end up with a ketone, for example. These are known as acyl transfer reactions. These are very, very important in biology, and we're going to talk about some biological importance of these today as well when we get into the next set of slides, okay? So, simple carbonyls like aldehydes and ketones do addition. Carboxylic acid derivatives can do addition elimination, which ultimately is an acyl transfer reaction, and that's important. Okay, so there are some differences. Now, one of the carboxylic acid derivatives that do this acyl substitution chemistry very, very well are the acid chlorides. So chlorine is our X group here. Chloride's a pretty good leaving group in these reactions. And so the nucleophile will attack. It breaks the weak pi bond first. You go through the tetrahedral intermediate, which then collapses. Chloride leaves, and you end up with your acylated nucleophile. So we call this an acyl group, okay? Whatever the nucleophile happens to be. What do you think the biggest mechanistic mistake is that students do in this reaction on paper? Pardon? They don't show two steps. A lot of students will look at this and go, oh, well, that's like an alkyl halide. It must be like an SN2 reaction, and show the nucleophile coming in and the leaving group leaving. But we know that that's not true. Why can't that be true? What do you think, Chance? Why couldn't we rationalize just having the nucleophile come in and the leaving group leave, all in one step like an SN2 reaction? What do you think, Blaine? Why couldn't we do that? If I gave you one of your friend's papers and I said, tell me, write on there to them why they couldn't do this, what would you tell them? Why would that be wrong? Okay, you could get into orbital arguments, but let's keep it fairly simple. Okay. I could push the arrows, though, that I could show the nucleophile coming in from the back and the leaving group leaving with arrows. I could do that, but it's wrong. Why is it wrong? What's the hybridization of the carbon that chlorine is on? sp2. And what did we learn about SN2 reactions on an sp2 hybridized carbon? It doesn't work, right? So, and it does have to do with an orbital argument, but you don't really have to get to that level of explanation. That's an sp2 hybridized carbon, and we know that that doesn't do SN2 chemistry. The other explanation is that the pi bond is weaker than a sigma bond, right? So it's going to attack the carbon of the carbonyl and break the weakest bond. And it's not the chlorine bond. It's the carbon-oxygen bond because it's a pi bond. So that one breaks first, okay? And so then once you have that, it reforms that weak pi bond and chloride is displaced and you end up with your nucleophile. And of course, you also end up with HCl as a byproduct in these reactions because our nucleophile typically has a hydrogen on it, so maybe this is like water. So if the nucleophile was water, what would my product be? It would be a carboxylic acid. That's exactly right. And so if you all were to come into my lab and open up a bottle of one of the acid chlorides we have, you would start to see white smoke come out of it because HCl is what? It's a gas, and in the presence of moist air, it's actually kind of a white, wispy vapor looking that you don't want to breathe, okay? And so these reactions release a lot of HCl as a byproduct, which is not healthy to breathe, so we have to do these in a well-ventilated fume hood, okay? And we typically add pyridine or some other simple amine base to soak up that HCl as it's generated. Okay, so the base then reacts with the HCl byproduct and forms pyridinium chloride, which usually precipitates out a solution, depending on the solvent you use, to keep that HCl from just going out into the hood and choking us all to death. So kind of nice thing to do. Now, acid chlorides can react with a variety of nucleophiles. Name a nucleophile, we can react an acid chloride with it, pretty much. Okay, are there some exceptions to that simple statement? Probably. For you all, probably not. Okay. So let's look at some of the things that we can react acid chlorides with. I can take an acid chloride and I can react it with the salt of a carboxylic acid, which we call a carboxylate. This is the nucleophile. This is the electrophile. We generate an anhydride product. Okay, so we can generate anhydrides by reacting acid chlorides with carboxylates. Is this a mixed anhydride or a symmetrical anhydride? Okay, if R and R prime are identical, it's symmetrical, but if R and R prime are different, it's mixed, right? So we can start off with an acid chloride here and a carboxylate that have different R groups, and we can get mixed anhydrides. We can react acid chlorides with water, and we can get carboxylic acids. We can react acid chlorides with alcohols, and we can get esters. How did you all make your ester? In laboratory. Did you use an acid chloride? No, you did not. What did you use? No, that was a reduction. You used benzoic acid, you used methanol as your alcohol, but what did you use? The man's going to his notes. I like that. What made the reaction go? If I take an alcohol and a carboxylic acid and I mix them together and I come back in 10 years, I'm still going to have an alcohol and a carboxylic acid. You did reflux it, but what else was there? What acid? You added sulfuric acid, right? That's right. Silver, no. So that's one way of doing the chemistry. Why did we have you all work the Fischer esterification route as opposed to using an acid chloride route? Do you all have efficient fume hoods sitting there taking away HCl gas? No, right? We don't want you working with those in that laboratory space because you don't have the hood space, the really good hood space to do that type of chemistry. So we have to pick experiments that'll work in the space that you're given. This reaction, do you suspect that this reaction is fast or slow? Very fast. Acid chlorides are very reactive. These types of reactions we love in my lab because you take the acid chloride, you dump it into an excess of the alcohol, and you immediately work it up. It's over. It's done, okay? You can take an acid chloride and mix it into water very rapidly and get a carboxylic acid, okay? And you can mix it with the carboxylate and you can get an anhydride, usually very quickly, okay? The reaction rates are quite high for these substrates. You can take acid chlorides and you can react with ammonia or other amines and you can get amides. If we use ammonia, we get a primary amide, okay? Why do we have two equivalents of the amine here in all cases? What do you think, Rose? Why do I have two equivalents of the amine? What's happening to the second equivalent? It's reacting with the HCl. That's exactly right. And so we have to have two equivalents because once we generate a little HCl, HCl is a what kind of acid? Strong acid, and an amine is a relatively good base, right? They react very quickly. Remember that acid-base reactions are among the fastest reactions that we know of. So it's not like the HCl is just going to sit around till the very end. It's very reactive once it's generated, right? And so we can prepare primary amides from acid chlorides if we have ammonia. We can generate secondary amides if we use what type of amine? Is that a secondary amine? It's a primary amine, right? And I can generate tertiary amides if I have a secondary amine, okay? We are making, in this process, peptide bonds. We are connecting, doing the same thing that Mother Nature does to make your proteins and peptides, okay? When your body is synthesizing proteins and peptides, do you think it goes through acid chlorides? No. There has to be another biological method for doing this, but the chemistry is essentially the same, okay? A practical use of acid chlorides is the manufacture of DEET. Anybody know anything in the media today why you might be interested in wearing some DEET this coming Zika virus, right? What do we know about that? Yeah, and how's it transmitted? Oh, really? Oh, well, DEET won't help you with that. So don't say Dr. Masterson said the DEET will take care of this, sweetheart, because it won't happen. All right? Zika virus. It causes birth defects. Does what else? Okay. Born with what?
It's like you have like a little head, like your brains are normally small, and then like it causes like seizures.
Oh, okay.
And developmental delays.
Well, you all definitely know more about it than I do. What else is another thing that mosquitoes transmit? Malaria. Yeah, these little mosquitoes that we have an awful lot of down here, and West Nile virus. That's exactly right. My dad actually lost a horse to West Nile a couple years ago. Huh? Really?
Yeah, he didn't realize it until he'd been working for like 3 days with it, though, and he had this giant rash all over his neck.
This is one of the easiest reactions to do. You take diethylamine in excess, which comes in water. It's a solution in water. And you just add the acid chloride to it, and you get DEET. And this is how SC Johnson makes this stuff, essentially, that they put in their product off, okay? It's through normal sophomore level organic chemistry. All right? And so I just mentioned to you that the diethylamine is actually in water. But didn't we learn that acid chlorides react with water to give carboxylic acids? So why do we only get the DEET out of this reaction? So Sarah comes in and she has, let's say, a 40 or 50% solution of diethylamine in an aqueous solution, and she adds that to the acid chloride, and she finds out that her yield is nearly quantitative in the formation of DEET. Why is that? We have two potential nucleophiles, right? Water and the amine. What does that tell us? The amine is a what? It is a much better nucleophile. And why is it a better nucleophile? Pardon? It's not a stronger base. No, that doesn't have to do with it. What's the difference between the nucleophilic atoms? Nitrogen versus oxygen, right? What can you tell me about that difference? What do you think, Jamie? So we're talking about the nucleophilicity of the nitrogen atom versus the water that this would be in. What do we know about the difference in those two atoms? Nitrogen's more electronegative? Oxygen. There we go.
That makes more sense.
That's right.
Okay.
So oxygen's more electronegative, so what's it doing to those lone pairs? It's holding onto them tighter, and nitrogen is not holding up onto them as tight, right? So it turns out that the amine is a much better nucleophile than water, and essentially the reaction goes to completion. You'll probably get about a 97% yield in this reaction, 98%, and the remaining part might be traces of the carboxylic acid. But nonetheless, the reaction works very, very well. So that's a practical use for this type of chemistry. And it's actually an amide bond. What kind of amide do we have? It's a tertiary amide, that's right. And it's a nice insect repellent, very effective against mosquitoes. I couldn't answer that question. DDT is, sure, yeah. But I don't know so much about the... Again, the mechanisms for these reactions are going to be an addition-elimination mechanism, right? So here we've got a carboxylate reacting with an acid chloride. We go through the tetrahedral intermediate. This then loses chloride as the leaving group, and you end up with the anhydride. You can take the acid chloride, react it with water. You get the same kind of chemistry occurring, and you get the carboxylic acid at the end after workup. Okay? It's an addition, which the nucleophile attacks the carbon of the carbonyl, breaks the weak pi bond. That tetrahedral intermediate is unstable, and it eliminates the leaving group, which in this case is the chloride, and regenerates the carbonyl functional group. Okay? So we can create a number of carboxylic acid derivatives from acid chlorides. Okay? So I want you to take just a minute, and I want you to use all the tools that you have at your disposal to figure out how to do this transformation. You have to start with that alkene, but you can use anything else you want, except magic. And there's more than one correct answer, by the way. Matt, don't go for the esoteric here. Just keep it simple. I know. You can get to Walmart on 98 via Canada if you'd like, but it's not necessary. Anybody know where Katie is today?
That's terrible. I didn't know. Harrison, just so you know, he doesn't ask that when you're not here. What did he say?
I do ask from time to time.
I'm a little hurt, but I'm not gonna cry. Actually, I'm gonna cry.
That's okay. I'm just kidding.
All right, let's think about this. So Mason, how do I need to approach this problem?
I converted that alkene.
Okay, you're thinking about Fords. How do we think about these problems?
Yeah, retrosynthesis.
We got to do retrosynthesis, right? So we got to look at the product. What do I know is the easiest bond to form in that product from everything that we know? That's the bond that we're going to need to form, right? And so in doing that, I've got two components. I'm going to have an alcohol component, and I'm going to have an acid component, right? So if I think about that, if I could get this acid chloride, which I said you could have access to anything else you wanted, so you could assume that that's there, right? And if I could get this alcohol, all I would have to do is mix them together with a little pyridine. Voila, I've got the product, right? This part is going to come from what? Mason.
Oh, DH3.
That's right. That's going to, I can get that from my starting alkene, right? So now, let's put it all together. So you took this and did what?
Boral trihydride, pH3, in CHF, and step 2, that was H2O and OH9.
That's right. And so what's the name of that reaction? That's the hydroboration oxidation. And what does it do for me? Anti-Markovnikov alcohols. That's exactly right. So now I can take that, mix it with my acid chloride, and I get the product, right? What would have been another solution? This works. What else would have been a solution? Grignard would know.
I think it could have worked.
You think it could have
Not
worked?
been pretty, but it could have worked.
Tell me how you would do it. I agree. You can get there through a Grignard reaction. Tell me how to do it.
I added
Okay, so you took the alkene,
HBr.
HBr, and what else do I need? If I do HBr, I'm going to get Markovnikov addition.
Yeah, you need anti.
So I need anti, and I can do that with HBr. What else do I need?
For HB.
I need some sort of free radical mechanism. Okay, so I'm going to pick peroxides, but strong light would have worked. You could have made the anti-Markovnikov bromide. And now what would you do?
I added a Grignard.
You added a Grignard.
I mean, I'm sorry. I added MG.
All right, so you made a Grignard.
Yeah, made
All
a
right.
Grignard. Sorry.
So you magnesium, ether, you made the Grignard. Now what do you do?
And then from there, I added, it was benzene attached with a double bond O and I think benzaldehyde or whatever, benzaldehyde.
All right.
Thank you.
And that would give me,
Wait, no, wait, not benzaldehyde. That wouldn't give me a double bond O. Or not a double bond O, it wouldn't give me an oxide right there.
CY is for cyclohexyl. Is that going to give me my product?
No.
No, I could oxidize that, right? And what would that give me?
Yeah, wait, opposite.
What would it give me? If I oxidize this, what would that give me? A ketone? Okay. I didn't say this was a pretty route. I just said it was possible. All right, so we get to the ketone. Now how can I make the ester from a ketone? You have the tool. It uses MCPBA. What's the name of the reaction? The Baeyer-Villiger reaction. And in theory, you could get that product. But the Baeyer vinegar can also rearrange to where it puts the oxygen between this carbonyl and this carbon, right? And so it'd have to look at migratory aptitudes. And you would end up with a mixture of products, actually.
Okay.
So on paper, could I get there through a Grignard?
Absolutely.
Yes. But I would argue that this is going to Walmart on 98 via Canada, right? This is a much more straightforward, more efficient method to get to the final product that you want to get to.
Okay. For the what we did, can we use bromates like a chlorine?
You can have acid bromides, but they're more expensive to make, and most people don't because the acid chlorides are already reactive enough. But you can make acid bromides. You can make acid fluorides even. And there's even some papers on making acid iodides. But the acid chlorides are almost always typically sufficient to do the chemistry you want to do. So.
Do you not need to react that secondary or that primary alcohol with NaH to make it like O minus and Na plus? Okay.
That is nucleophilic enough in this reaction. The acid chloride is so reactive, it'll react with the neutral alcohol. So we do not have to convert it to an alkoxide first. Will it react with an alkoxide and do it? Yes, but why do it? It's more work. Okay? We already talked about that. All right, we're going to continue talking about some of the chemistry of acyl substitution, again, because it is so important in biology. It's important in polymer chemistry. It is an important reaction in general that you need to have a good grasp of as you decide to move further in your studies in your various disciplines. Okay? One of the things that amides can do is they can hydrolyze. You can take an amide and you can react it with water in the presence of acid or base, and you can get carboxylic acids or carboxylates. You can break the carbon-nitrogen bond in doing so. Do you suspect that that reaction is fast or slow? It is. Can you tell me why you feel that, or what leads you to believe that? That would be a problem. Okay, so you're using your common knowledge of biological materials to make that assumption, and it turns out to be correct. What other chemical assumption can we make that tells us that that ought to be slow? What do we know about resonance structures of amides? They do exist, all right? We can push the lone pair of electrons from the nitrogen, right, onto ultimately the oxygen and put a carbon-nitrogen double bond there, right? So does that mean that the carbon-nitrogen bond is going to be stronger or weaker than expected? If I can have a resonance structure that makes it a double bond structure, is that going to strengthen it or weaken it? Strengthen it, that's right. So we expect that these amides are actually fairly strong bonds because of what Gabby was telling us. Our normal experience tells us that our proteins are built with these bonds for a particular reason, and it has to. And we are water-based, right? We are nothing more than dirty bags of water, right? So there's a lot of water around, and these proteins last an awful long time. They hold up to that. So to get this reaction to work, you have to go to really acidic pH, which is outside the realm of biology, or you have to go to real basic pH, which again is also outside the realm of biology, and you really have to, what we say, beat on them to get this to work. Now there are catalysts that are available that can speed this reaction up. Your body has catalysts that can speed this reaction up because you do break down proteins in your gut to make the amino acids that you need to synthesize the proteins that you want, right? So when you eat a piece of meat, it's not the cow's proteins that get incorporated in your body, right? It's the amino acids from that meat that you eat that end up getting incorporated into your body's stuff, okay? So this reaction is actually fairly slow. It's easy to write on paper. It does work, but it sometimes takes a long time to get these things to hydrolyze. And we can understand that a little better if we look at the mechanism. All of these steps are reversible except for the last step. So this is under basic hydrolysis. The hydroxide attacks the carbon of the carbonyl, breaks the relatively weak pi bond. You end up with the tetrahedral intermediate. Are you seeing a theme here? There's a lot of tetrahedral intermediates, right? Now the tetrahedral intermediate collapses and we lose NH2 minus. That's the bad step, is that loss. Can anybody explain to me why that's the slow step? The slowest of the steps. Why is that so slow? You remember that little paper I gave you early on from JChemEd on pKa's and why pKa's are so important? What do we know about the pKa of an alkoxide? Just a typical alkoxide. Give me a rough range. What do you think, Karina? What would be the typical range for a alkoxide for a pKa value? Nine's way too low. Still too low. Way too high. We've set the limits here. It's around 19-ish. 19, 20, 18, somewhere in that ballpark, okay, for an alkoxide. What's the pKa value for an amide, NH2 minus? Higher or lower? Higher. By what, a little bit or a fair amount? By quite a little bit, yeah, fair amount. So we're taking a weaker base and generating a stronger base. Is that how equilibria lies? No, we always lie to the weaker acid, weaker base pair, right? So the equilibrium actually lies here, and this is actually fairly slow, okay? But once this happens, this is a strong base. This is, relatively speaking, a strong acid. The chemistry occurs, and you end up generating the carboxylate and ammonia. Okay, so ultimately it does lie to the weaker base after this step happens, okay? But getting here is the slow part. And so this proton transfer, as we call it, happens. Ammonia is a gas, it blows out. Le Chatelier's principle drives the reaction to the right, but it is a slow reaction, okay? Beta-Lactam antibiotics, this is a structure of penicillin. What's the pharmacophore? We talked about this on Monday.
That's the part that makes it
Okay, what functional group in there is the pharmacophore? The strained ring. That's right. Which one is the strained ring? The four-membered ring. And we call this four-membered ring with an amide a what? That's a beta-lactam. That's right. Penicillin is a beta-lactam antibiotic. It has other stuff. It has a regular amide. It has the strained amide, if you will. It's got a carboxylic acid. It's got a sulfide. It's got stereocenters, which are all important. Okay. It's made by a mold, right? Penicillin. And all the cillins contain this strained amide ring.
Now, if someone is allergic to penicillin, is that the part they're allergic to? Or the beta-lactam, is that the part they're allergic to? Or could they be allergic to different sections?
It turns out that you can't technically be allergic to small molecules. What happens is that the penicillin reacts with your proteins and modifies them, and that's exactly what you're allergic to. So, yeah, you are allergic because of what it does, and it's the product of the reaction that it has that you're actually allergic to. Your body really can't generate antibodies to small molecules by these types of small molecules in of themselves. And so that's, if you take my medicinal chemistry class, that's something that we actually talk about quite a bit. So it's the modified proteins that you're actually allergic to. The way that this works, you all know how a bacterial cell works, right? You have a cell wall, right? And it's that cell wall that keeps its integrity, right? And keeps it resistant to a lot of medicines that we use. And the way that these cell walls get to be strong is that one strand of the polymer chain and another strand of the polymer chain, one has an amine, one has a carboxylic acid, and there is an enzyme called transpeptidase, which catalyzes the formation of the amide bond. Notice it's not an acid chloride, but the transpeptidase actually reacts with the carboxylic acid to make it a better leaving group. Then the amine reacts and you get this cross-link. And we know that this is a very strong bond, so it holds the cell wall together very, very well. So what does penicillin do? Penicillin goes in and messes with transpeptidase. It shuts it down. And if you shut down transpeptidase, the cell wall will be stronger or weaker? Weaker. And if it has a weak cell wall, what do you think your own body's defense mechanisms can do? It can attack and kill the cells, okay? And so that's how penicillin actually works. It breaks down the defense of your infection, okay, and allows your body to do its work. It doesn't really go in and directly kill the cell itself. It weakens its defense so that you can go in and do the chemistry on it that you need to do, okay? And so the way that this works is in the transpeptidase active site, and don't worry too much about that, there's a primary amine. That primary amine reacts with penicillin and gives this structure, which is dead. This is a catalytically inactive form of transpeptidase. So what you've done is you've taken the reactive part of transpeptidase and you've put a protecting group on it. That's essentially what you've done. You've protected the amine as an amide. And now it can't do the chemistry that it needs to do with the cell wall, okay? And so that shuts down the enzyme, the cell wall is weak, and your own body's defense mechanisms can go in and kill the infection. Now, that's oversimplified, but that's essentially what's happening, okay? So you're inactivating the enzyme and allowing your body's natural defenses to do their job, okay? We depend on that strain in that four-membered ring for this to work, because typically an amide is a very stable bond, right? But in these four-membered rings, because of ring strain, they're more reactive, okay? So you all have heard of penicillin-resistant bacteria. How do they become penicillin-resistant if this stuff goes in and kills the transpeptidase? What is the bacteria doing in response to that evolutionary pressure that we've applied? But how? That's right. So if you take only a partial dose of your penicillin, you kill off everything that's going to be susceptible to the penicillin, and the things that remain have genetic mutations, right? That maybe their transpeptidase is a little different, right? And so then what happens to them if they don't die off? They multiply, right? And so through an evolutionary pressure, you can actually get enzyme or antibiotic resistant bugs because they have enzymes that won't go through this deactivation process, okay? This is a nice little chart in terms of knowing the reactivity of things. So acid chlorides will react with a variety of things and make products, right? So acid chlorides, you can make anhydrides, acids, esters, and amides. From anhydrides, you can make carboxylic acids, esters, and amides. From carboxylic acids, you can make acid chlorides. How do we do that? What's the reagent? A carboxylic acid plus what gives me an acid chloride? HCl won't do that. Sulfuric acid won't do it. Do you all remember thionyl chloride? Thionyl chloride will react with carboxylic acids to make acid chlorides. Okay? So this is a nice little chart to kind of show you the various things that you can make from these carboxylic acids. Some natural fibers that exist with these amides, proteins. So wool and silk, for example, if you like silk clothing, you're actually wearing a protein. If you like wool clothing, you also have a number of amide bonds in there as well. Okay? Nylon. What do we use nylon for? A lot of things, that's right, but it's specifically like rope. This is used in the maritime industry on ships, and we no longer use natural fiber ropes on ships. Why is that? They degrade in the presence of salt water. Over time, not immediately, right? But what about nylon ropes? They hold up pretty strong because they're completely amide-based. Okay, so this is an example of nylon 6,6. Okay, I'm going to stop there for today. This slide is as far as we're going to get to on the exam next week. So Monday we'll have a review session, right? In class, I will try to schedule something for Tuesday as an additional review session, and then we'll have the exam on Wednesday. Please go ahead and turn in your little note cards I asked you to do for the mechanism of the ring open, ring closed form of the sugar from the demonstration last time. Oh, that's fine. Yeah, if you got it, whatever you got it on.